Welcome back to Physics 141 Online. Thus far, the kinematic equations that we've worked with in class are only for the situation where an object is moving in a single direction with a constant acceleration. But sometimes we might have situations where the acceleration is not constant. And so it's useful to have a mathematical method for handling situations like that. And calculus allows us to create a method for starting from an expression for the position as a function of time, x of t, and calculating the velocity in that direction. And then from the velocity function, we can calculate the acceleration function. And this could involve cases where the acceleration is changing. So you will learn how to do this rigorously in a calculus course, but right now all I want to do is present the results. And I'll just remind you what these results mean graphically and how we write them down. So in calculus notation, the velocity in the x direction is referred to as dx by dt, and we sometimes call this the derivative of x with respect to t. What it means graphically is it's the slope of the position versus time graph at an instantaneous point in time. So this is the instantaneous velocity. Likewise, if we know the velocity as a function of time, then the acceleration is the change in velocity with respect to time. We read this as dvx dt, or we can call it the derivative of v sub x with respect to time. And it means the slope of the velocity versus time graph at a specific point in time. The results for how to do this for polynomial functions are very straightforward. And like I said, I'm not going to derive them or show you where they come from, but just show you the simple result that you will get to in a calculus course if you haven't done that yet. So imagine that we're given for an object, perhaps we've observed this object, and we have a simple function that describes its position as a function of time, where x of t is equal to some constant b times the time variable to the nth power. So this kind of a simple polynomial, or a sum of polynomial terms like this, can be used to calculate the slope or the velocity as follows. So we would write this as d btn by dt, and here's the result. What happens from the original function is the term that's in the power, the n, comes down in front to multiply b, and then the time variable gets raised to one lower power than it originally was. So x was equal to bt to the nth power. V sub x will be nb times t to the n minus 1 power. It's a simple rule, and it's actually not that difficult to derive, but I'm not going to take the time to do that here. So let me do a simple example without using units to keep it really simple. So imagine that we're given that there's an object that's moving where its position at any time, we can plug in any time value whatsoever, and we can get its position. But it's given by the formula 4t plus 6t squared. And so, if that's true, the velocity would be v sub x is equal to dx dt, and from this expression 4t plus 6t squared, the first term, the power of t is 1, so 1 times 4 times t to the 0. That would be the derivative or the slope of this first term. And we'll simplify that in just a second. The second term, 6t squared, well, the 2 comes down in front, multiplied by the 6 times t to the first power, which is 1 smaller than it started. And so the first term, 1 times 4 times t to the 0, just gives us 4. Remember, t to the 0 is the same as 1. The second term gives us 2 times 6 times t to the first, or just 12t. So we started with the given function for position as a function of time, and now we've calculated velocity as a function of time, and we can go one step further. Now, taking this expression for the velocity as a function of time, we can calculate the acceleration. The acceleration is the slope of velocity versus time, or the derivative of velocity versus time. They mean the same thing. The first term is a constant, and a constant term doesn't change in time, and so the derivative of that is 0. The slope of a constant function is 0, right? The second term, 12t to the first power, well, the 1 comes down in front, multiplies by 12 times t to the 0, so the acceleration turns out to simply be 12. Again, I'm not worrying about the units involved in this problem. Notice here that this turned out to be a situation where the acceleration, after we calculated it, was a constant. But that may not always be the case, and I'll show you next an example that's a little more complicated because it is asking us to do some calculations involving units. Also, we'll find out that this is a calculation that produces a result where the acceleration is not a constant. So this is a homework type of problem. You'll have something similar to this on your homework. Assume that an object's position is given by the function x equals bt cubed. X is in meters, t is in seconds, and b is a constant that has this value in these units. And we want to do a number of things. I'm just going to work through the first two questions here. The last two don't involve calculus, and we'll just skip those for now. But determine the instantaneous velocity at the end of 2.9 seconds, and then the same for the acceleration. So let's do part A. We know the expression for position. We can use our rule for how to take the derivative or the slope of a polynomial function to get the velocity, and then, once we do that, we plug in a specific value of t, 2.9 seconds. So part A, Vx is dx dt, and since x was bt cubed, the derivative is 3, the 3 comes down in front, times b times t squared. Because the t cubed now, the power becomes 1 smaller. So that's the general expression, and that would give us the velocity at any time t that we plugged into that equation. All right? And that's what we're going to do. We're going to plug in the value t equals 2.9 seconds. So now what we're doing is calculating a specific value of the velocity at a specific time. So at 2.9 seconds, we just plug in, we got 3, b is 2.0 meters per second cubed, t is 2.9 seconds. Remember, it's squared. Got to be careful with the squared term. And if we numerically crank that out, we get 50.5. And be careful with the units. You have meters per second cubed times seconds squared. And if you work that through carefully, you see that gives meters per second. And that's a good check. We always want to carry units along because we got meters per second, which is consistent with a velocity. And that's what we're trying to calculate. So that gives us some confidence that we did the calculation right. Now what if we want to calculate the instantaneous acceleration at that same time? Well, we wouldn't use the 50.5 because that was simply a specific value of the velocity. What we have to do is go back to the general expression for the velocity as a function of time, which is 3bt squared. So the acceleration is the derivative of this, and the 2 comes down to multiply the 3, giving us a 6. b is still there, and the time is now to a power that's 1 smaller than it was before. So when it was 3bt squared, now it becomes 6bt for the acceleration in the x direction. And we plug in t equals 2.9 seconds to get 6 times 2 meters per second cubed times 2.9 seconds. The numerical value is 34.8, and the units, meters per second cubed times seconds, gives meters per second squared, which is appropriate for an acceleration. That's another useful check to make sure that we did the calculation right. And notice here, like I said a few minutes ago, this was a problem where the acceleration was not a constant because it had a time variable in it. So this was an object that's moving where its acceleration is increasing with time. And we didn't have to use any of our kinematic equations to apply to this. Matter of fact, we couldn't have done that because they only work when the acceleration is constant. So as I said, we'll skip over C and D for now, but I hope this gives you some simple applications of calculating slopes or derivatives that enable us to start with position and calculate velocity and acceleration from that. And I will see you in class.